All right, exponential functions. So the first thing we're going to do is everything in this, obviously this lesson is going to be exponentials, and then we'll get to logarithms later on. But today's lesson is just that. So just a quick review. As long as you have the common base, so notice that both bases are a's, then what we do with those exponents, when we multiply common bases, we add the exponents, so s plus t. If we had a to the s raised to the power of t, so a lot of times you've heard this as power to the power, so s to the t, we would take s and t and multiply them. So we keep our a, that base the same, so it'd be a raised to the s times t power. If you have a and b multiplied or divided for that matter, but not addition subtraction, or that goes to distribution, expanding. This is just taking your exponent and you can put it on each piece in those parentheses. So the s can go on the a and it can go on the b. And then just some other quick ones. If you had 1 raised to any power of s, it's 1. A to the negative s, we would write that as 1 over a to the positive now power of s. And then anything raised to the power of 0 is 1. All right, so our first problems we're going to look at solving is if we had, for instance, 4 raised to the power of 2x minus 1 equal to 8 raised to the power of x. How would we solve that? If you may remember this from last year, but if you don't, it's okay. But what you need to do is we need to have common bases, then we can use all these properties we're just not talking about up here. So right now our base is 4 and 8. So we need to think of a number that we can change both of those into so they're both the exact same number, the same exact base. Here's what I mean by that. The 4 you can change to 2 squared. And the 8 you can change to 2 cubed. So now they have the exact same base. They're both 2's. Now 2 squared represents our 4. I'll put that in parentheses. So the 4 you can see is right here with the 2 squared. The only thing that's missing is our exponent that we had from the top, which is 2x minus 1. So if 2 squared is 4, the 2x minus 1 would be on the outside right here of our parentheses on our exponent. Same thing over here with our 8. We know 2 cubed is 8. So the only thing we're missing is this x. So we'll put that x right there in our exponent. So now we're going to use a power to a power. So if we have those two pieces, we can multiply them. So 2, our base, raised to the power of 2 times 2x minus 1. And the same thing on the other side. We'll multiply the 3 and the x. So 2 raised to the power of 3, 2 raised to the power of 3x. Now, we now have the same exact base. Both of them, these are 2's. What we want is our exponents to be the same. Because if they were the exact same, then obviously we would have 2 raised to a power equal to 2 raised to the exact same power. So we just need to figure out what value of x would make that happen. So from here, we just take our exponents, so 2 and 2x minus 1, and we're saying when would those be the same? For what value of x would those exponents be the same? And it's just a matter of solving the equation. Distribute, so we have 4x minus 2 is equal to 3x. Move our 3x over by subtracting, add our 2 over. So when x is 2, we know that 4 raised to the power of 2x minus 1 would be equal to 8 raised to the power of 2. And you could check that out and plug it into the original equation, and you can verify it and see that it is in fact true. All right, let's go to the next one. E to the negative x squared. And then we have e to the x squared times 1 over e cubed. So the first thing that's nice is we notice that e, this a number that's approximately 2.718, is already their base. So that's kind of nice. It's just a matter of rearranging everything. So e to the negative x squared, let's leave that alone for right now. E to the x raised to the power of 2, well, that's just e to the 2x. And notice that since e is already the base, I'm going to leave it alone, and then look at this e to the third, and I want to get it to the top so that it also looks like the other two pieces we're dealing with. And that would just mean that we had to make it a negative 3, going back to like our negative exponents. So we bring the e to the third up, it becomes a negative exponent. Now we're multiplying common bases, which means we can add their exponents. So e to the negative x squared is equal to e to the 2x plus -3, so -3. And now right back where we were at earlier. We have a common base of e, and we have these exponents that need to be the same. So now we can say -x squared and 2x minus 3 need to be equal. I would go ahead and move that x squared over to the other side by adding. And then it's just a matter of solving our quadratic, in this case factoring. Looks like it's going to be x plus 3 and x minus 1. So x could be 1, or x could be -3. And once again, you could probably go up there, plug them in, verify it, make sure it works for both of our solutions. All right, so part C. If 5 to the -x is equal to 3, what does 5 to the 3x equal? So we're looking at the same, type of setup here. We're trying to say, okay, if we have 5 to the -x equal to 3, and we have this, this piece over here, so first thing I do is just go ahead and write that with our equation. And there's a couple ways we could go about solving this problem. The first one I'll do is this. So you could think of it as 5 to the -x. And what we're going to do is we're trying to build it. So we're going to make this 5 to the -x look like the 5 to the 3x, because we're trying to get to what is 5 to the 3x power. Well, if we want to change this and make it 3x as our exponent, well, we'd raise this to the power of -3, because we know that we would multiply these. Negative and negative make a positive, so we'd end up with 3x as an exponent. But if we raise one side of our equation to the power of -3, we need to do the exact same thing to the other side. So now we have both of our sides of our equation raised to the power of -3. Well, we can multiply that. So now it's 5 to the 3x. All right. And then this would be 3 to the power of -3, which remember that would be the same thing as, right over the side, 1 over 3 to the power of +3. So 1 over 27, which is exactly what we're looking for, 5 to the 3x. So we know that 5 to the 3x is equal to 1 over 27. And that's one method. And I think it's worth saying, if you didn't see it that way, maybe you might have done it this way. I'll just go ahead and write it out, just in case you didn't like that way. Maybe you would have thought of it like this instead. 1 over 5 to the x equals equal to 3. Multiply that 5x over. So it's now 3 times 5 to the x is equal to 1. Take this 3, we can actually divide it. So we're saying 5 to the what power of x would equal 1/3. Well, we know that we're looking for 5 to the 3x. So I'm just write it over here so you can kind of see it. So 5 to the 3x is the exact same thing as 5 to the x raised to the power of 3, right? And we know that 5 to the x is 1/3, so we can substitute 1/3 in place of that 5 to the x. So we're just going 1/3 raised to the power of 3, which is the same thing as 1 over 27. So I just thought I would give you a couple different methods of looking at that particular problem. All right, here's the last one, this section. 9 to the 2x, well, we can change, we want, first of all, 9 and 27 to have the same base. So we know that we would have 3 as our base. So 3 squared would be 9, raised to the power of 2x. And we're going to multiply that times 3 raised to the power of 3 will give us 27. And that's x squared. And then all of that's equal to 3 to the power of -1. So we can go ahead and change this to 3 to the 4x. times 3 to the 3x squared. Common base, so now we can combine that into one expression, if you will. So 3 is our common base. We would take 4x and 3x squared and add them. And we have the same base. We need these exponents to be equal. We're going to rewrite that as 3x squared plus 4x equal to -1. So we have 3x squared plus 4x plus 1. Obviously, we're hoping this factors. So we have 3x plus 1 and x plus 1 equals 0. So we know that x is -1/3 or x is -1. And there's our two solutions. It's always a good idea to check them. Just good practice. But there's that first section. Okay, so now what we're doing is we're going to look at how these transformations would compare with our parent function. So these next four, our parent function is 2 raised to the x power. So for exponents, they can be, for exponents, they can be a lot of different things, depending on what our base is. So right here, our base is 2. So one thing, before I dive into these, I do want to come over here to the side. You'll see it under notes, but this is kind of like a general form for exponents. And luckily, it follows the exact same, rules and principles that we've done on all other functions. If this was a negative right here in the front, this would cause to be, a reflection across our y-axis. Positive, obviously, just staying put. A is going to be our vertical stretch slash shrink. See if I can fit it all in here. So there's our vertical stretch and shrink. B is obviously our power that we're working, or our base that we're working with. This is our minus h. I don't know if that looks very clear, but our minus h right here, that's our shift, left or right. So I'll just abbreviate it. So that's our shift left and right. Remember, we always think opposite with x's. And our last one is our k. Not sure if this will fit in here, but I did it down here. That would be our shift up and down, our vertical shift, which is going to come in handy. It's just moving our graphs up and down. When we get to graphing, it really does help us with some asymptotes. We'll talk about that momentarily. So looking at our first one, 2 to the x power plus 1. So really the only thing we're doing here is we're adding 1. Everything else is staying the same. So that's our vertical shift. So just to compare, we're going to be shifting that up. Right, just to shift up 1. That's the only thing. That's the only way it compares to our given parent function. All right, next problem. This one might be a little bit weird looking because we have a 1/2 instead of a 2 right there. And that's what's pivotal, because remember our parent function that we're comparing everything with is 2 raised to the x power. But that's okay, because the only thing we need to do with this is just change it where it is a 2. And we know that if we put 2 to the -1, 2 to the -1 would produce a 1/2. And we're just having our x still out there on the outside of our parentheses on the exponent. So just to rewrite this again, we'd say 3 times 2 to the -x. And now it looks a whole lot like our parent function. So our 3 would be our, our vertical stretch. Right? By a factor of 3. I'll just say by 3, so by a factor of 3. So if we were going to, you guys like transformation tables, that's where we would take our y values and multiply by 3. We'll do that momentarily. And the -x, that negative actually takes it and it reflects it. Right, it's a horizontal reflection, so it reflects it across the y-axis. If the negative was in front, it'd be across the x-axis, but since it's on the x, it's actually a reflection across our y-axis for that particular problem. All right, next problem. I would probably rewrite this and put the negative 2x minus 3 right there in the front, and then put our 1, add our 1 at the very end. And then we're just kind of following along. We know the negative is going to be a reflection. So it's going to be reflection across our x. The minus 3 is actually going to shift our graph not left, but right. 3 units. And then the plus 1 is going to shift it up. All right, so you can say shift up, I guess. Shift up 1. So there's our 3 transformations for that problem. Okay, so do the exact same thing with this problem. We write it as negative 2 to the negative x over 3 plus 1. And then just go down the line. I like to go from left to right typically. And I'll go ahead and write this. Maybe this will help see it. I'll just kind of look at this problem. Maybe if I wrote it as negative 1/3 x, I don't know if that makes much of a difference, but just in case, I'll rewrite it like that. It'll help see some things. First of all, we have our negative in the front. So there's our reflection. And across our x-axis. And then our negative right here on the 1/3 is actually going to be a reflection also. Across the y. Okay, now just looking at the 1/3 in itself, remember everything's opposite with the x's. So we know there's going to be some type of horizontal shrink or stretch. In this particular case, it's actually a stretch. And I think I can fit this in on the camera here by 3. So remember, you just take that 1/3, you do the reciprocal of it. It's always kind of the opposite thought process. So you would take, if you just think of it more in terms like our transformation table, when we do those here in a little bit, we would take all the x's and multiply them by 3. And our last one is we're going to do is shift our graph up 1 unit. So we have 4 things occurring on that particular problem. Okay, so let's do a few graphs. We're working with, this would be kind of our parent function for this particular section for a and b. So f of x is equal to 2 raised to the power of x. So, if you're picking values for x, 0 would be a good one to pick. And we can count, 1, 2, and continue down all the way to 3. Those would all be good values. And I left one more space up here just to kind of see what's going on in the negative direction as well for our x's. So as you plug those in, if you plug -1 in place of x, you get 2 to the -1, so 1/2. And then obviously just keep on going. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. And then 2 cubed is 8. So now we can go over here to our graph and we can plot those points. You have a little bit better graph than me, maybe, if you're able to print it off. If not, it's okay. You can just kind of do what I do. We're looking at 0, 1 right here as a particular point. And then we have 1, 2. So 1, 2, it's about right there. And then 2, 4. 3, 8. And then we get our negative direction. So negative x at 1/2, that's about right here. And if we continue to pick on more negative directions, if you put in -2, for instance, for x, you get 1/4. And you put -3 and you get 1/8. -4, you get 1/16. So it's just going to keep on going down, getting really, really, really close to 0 without touching it. So this is our exponential graph. So I'm going to go right through here, pass through those plotted points that we have. And then our x-axis is important this time because, like we said earlier, it's going to get really, really close to our x-axis, but it's not going to touch it. So this is actually going to be like a horizontal asymptote right here, that red line I've drawn in. And it's y equals 0. All right, so just kind of interesting questions down here. It tells you that the pivot point 0, 1. I'll just say this about pivot point. It's basically just when our graph kind of quote unquote takes off. You know, it's really flat. And then right here at 0, 1, it really starts to curve up pretty sharply. Not a big deal, but just kind of something worth mentioning. Let's just kind of look and see here. What's that next part again? We're looking for exponential growth or decay. The 2 is bigger than, it's a large number. It's not a fraction that we're working with here. Okay, it's actually larger than 1. And the graph, you can see it's going up actually. So from left to right, it's increasing. So this is a exponential growth. I'll write the word all the way across this time. So exponential growth. You also have to enter the domain and range. Domain is just all real numbers. So negative infinity to infinity. Our range, this is where our horizontal asymptote comes into play. It doesn't get to 0, and obviously it doesn't go below 0 for our y values. So the lowest y value we get to is almost to 0, and then it goes up forever. So we're going to say our range is from 0 to infinity, and our horizontal asymptote is y equals 0. So you can see there's already kind of a connection most likely between the horizontal asymptote and the range. They're going to kind of complement one another and help us determine one or the other, given whatever particular problem that's thrown our way. All right, continue on. So now we have some transformations going on. And if you notice, it's the exact same basis of problem we had before. So I'm actually going to just use a transformation table. And I copy this transformation table to look like your notes. I'm going to list out the same x's. So 0, 1, 2, and 3. And negative 1. And this first column, I'm going to use that for just the x portion. So all the x, only thing that's happening to our x on this particular problem is we're going to take our old x's and we're going to add 3 to them. Remember, we always do the opposite of what's given to us in our equation. So since it's minus 3, it means we're going to add 3 to all of our x's. So negative 1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. We'll just continue on. 2 plus 3 is 5. And then we'll finish off with our last one, 3 plus 3. It wasn't a column given for the y, so I'll just kind of work that y right here, and we have to make sure we go back to our previous problem and use those. Let me go ahead and just write those over to the side. Now you can probably see it, but our old y's were what, 1/2, 1, 2, 4, and 8. Okay, so these were our old y's from earlier. So just kind of taking from a transformation table standpoint, the negative in front means we would take our y's and we would multiply them by negative. And the other thing we're going to do is shift it up 4 units. So we'll just take all of our y's. We're going to take that, make it negative 1/2. And negative 1/2 plus 4 is 3.5, 3.5. 7 halves, if you will. Okay, do the same thing with the 1. So negative 1 plus 4 is 3. Negative 2 plus 4 is 2. There's going to be a 0. Our negative 4 plus 4. And then if we plugged in 8 in place of the y, negative 8 plus 4 is negative 4. So just to make sure we understand, there's a lot of stuff going on here. This column right here and this column right here are our important columns. This first column right here that I have highlighted, that's our new x values, and these are our new y values for our graph. So once again, I'm just going to kind of freehand it a little bit. 2, 3.5. No, we have to go all the way out to 6. So go ahead and just kind of put all those out. 3.5, roughly right here. 3, 3, 4, 2, 5, 0. There's our x-intercept. And then 6, negative 4. And we could actually look and say, well, what's going on here to the left as you start picking more values. And you would notice that this graph is going to start to kind of flatten out pretty quickly. Now, where does it flatten out is kind of a question, because that's an important piece. And that's kind of what I wanted to look at right here. If you look at this +4 here at the very beginning, and I think I mentioned this earlier, but this +4 is an important piece for us, because it's basically taking our graph and just shifting it up 4 units. It also tells us where our horizontal asymptote is going to be, because typically, let me go back up to our parent function from earlier, our horizontal asymptote is at y equals 0. So if you had any type of vertical shift, it's just going to shift your horizontal asymptote as well. So a lot of people, what they do on these problems is they actually graph their horizontal asymptote first. If you find that's helpful, that's fine. Or you can graph it at the end, whatever's better for you. But since we know our graph is shifted up 4, I'm going to draw this in red. We know that we're going to have a horizontal asymptote right here. Y equals 4. So that's what our graph is going to be approaching. So it's going to come from this direction. And there's our graph we have. Reflection shifted right 3, up 4, based on our y equals 2 the x parent function. And so then it's just a matter of answering the questions at the bottom. Our pivot point, it kind of starts to turn right here at 3, 3. You remember, you can look at it and see, well, that's one that matched the 0, 1 from earlier. So our pivot point is 3, 3. Not a huge thing, to be quite honest with you, but I'll go ahead and answer it since it's on the notes that we made for you. It's just to kind of help you on my math lab. We structured it for my math lab. Domain, everything. So all our numbers. I'm going to do range. I do horizontal asymptote. So now our horizontal asymptote is y equals 4. It's a horizontal line. And our range, it goes down forever, but doesn't quite get up to 4. So negative infinity to 4, non-inclusive. All right, part C. Now we're going to have f of x equals e to the x. So it's a different base than we were dealing with earlier. This is the e value that you're going to see a whole lot in calculus. It's very common in applications. It's kind of like pi. It's just a very common irrational number that's used for a lot of application problems and in the real world per se. So here's x and y in our table again. It comes and do the exact same values from earlier. If you were to plug in, -1, you would get e to the -1, or 1 over e, and then e to the 0 is 1. E to the first is e, which is approximately 2.718. And then we'll have e squared, which is approximately 7.389. And then e cubed, which is going to get pretty big. It's probably 20.086. And so on and so forth. So I mean, it climbs pretty quick, obviously, being exponential. So just do the same thing we did earlier. 0, 1 is an important point. And then we have over here at 1e, so 1. And then we have 2.718, so roughly in there. Okay, and then 2, so we can fit that in there. I'll go a little higher here. Is it 7.3? And then we have our -1, and then 1 over e. Oh, sorry, I went in there. Right here. -1 is 1 over e. So disregard that first little point I put in there. So it's going through. There's our graph for e to the x. Pivot point, still 0, 1. Domains, all real numbers. Range, well, this is the same thing as when we had 2 to the x. We had that horizontal asymptote at y equals 0. So I'm going to go in here and put y equals 0 for our horizontal asymptote, which means our range is everything from 0 up. And then we have our limits. I think the first one in your notes is limit as x approaches infinity. So which, as x approaches infinity, as x gets larger and larger and larger, the y bay we're approaching is, well, it's going to go up forever. So its intended y bay in this case would just be infinity. And then if we have as x approaches negative infinity, so as we go over here really far to the left, the y bay that we're getting closer and closer to, the one we're approaching, is 0. Okay, our final graphing one. Got everything set up. Hopefully that'll save some time. But once again, taking this middle column and just using it as our transformation table for the x. So we're adding 3, remember that means we're going to take our x values and subtract them. We always do the opposite. So we take -1, subtract it, so it'd be what, -4, -3, 1 minus 3 is -2, -1, and then 3 minus 3 would be 0. All right, then for our y's, we're going to multiply them by -1 because of that negative in front of the e. And then we're going to shift it up 1, so add 1. So just taking our old y's listed over here to the left, it'd be 1 over e, or -1 over e plus 1, which, it'd be some nasty decimal, but we can write -1 over e plus 1. And then we'd have 1, -1, right? Because plug the 1 in for the y. -1 plus 1 is 0. Let's see here. This would be -2.718 plus 1, so -1.718 approximately. This would be -7.389, so -6.389. And then you could get that one too. I guess it'd be obviously pretty far off the graph, -19.086. But I'm not going to plot that one. It's just a little bit too big. So the important columns here. Here's our new x's. Here are our new y's. Which I'm just going to plot a few of those. Go back up here to our +1. Remember, that's going to be our horizontal asymptote. So I didn't do this earlier, so I'll just go ahead and do it this time. So I think it might help a little bit. This is plot that horizontal asymptote. Remember, it's just to shift up 1 unit. From our normal horizontal asymptote, which is y equals 0. So just throw that in there. Let's see here. We have -4. And I'm not going to plot that one. So -3, 0. Okay, there's that point. -2, -1.78. That's about right here. -1, -6.389. That's about right there. And then obviously it's going to decrease pretty quickly. It'll get finally to 0 at -19. So it's going to be way down here. And then we know this -4, which I didn't plot earlier, but it's not going to be, it's going to be below 1. We know that for sure. Okay, it's just going to get really, really close to that horizontal asymptote that we graphed previously. And then our graph's going to continue to decrease, go in that direction. Make sure I kind of draw it a little better. It is definitely going to cross the x-axis, or the y-axis rather. It's going to continue moving to the right. Pivot point, Remember, our pivot point from earlier was 0, 1. So this one's going to be negative 3, 0. It kind of just matches with our 0, 1 right here. Domain. This graph goes to the left and to the right forever. Our range, it goes down forever, but it doesn't reach, it doesn't go any higher than 1. In fact, it doesn't even touch it. So it's negative infinity to 1. Horizontal asymptote, we graphed that earlier. Remember, just that vertical shift that we do. The limit as x approaches infinity. So as we go to the right forever, keep on going to the right, what y value are we approaching? Well, what's going down? So it's going to be negative infinity, and as x approaches negative infinity, for this last limit as x approaches negative infinity of f of x, as it keeps on going to the left forever, the y value is getting closer and closer to its approaching is 1. All right, so let's finish up with some mixed practice problems. This is the final portion of your notes at the bottom. So let's suppose that f of x is equal to 2x. We're going to answer a bunch of questions based upon this stipulation right here at the beginning. So f of 4, just simply plug 4 in place of x. So what's 2 to the 4th, which we know is 16. Just kind of save some space. I'm just going to write it like that. What point, so basically just saying, what point would f of 4 represent on our graph? Well, the x value is 4, and then we determined our y value of 16, so it'd be 4, 16 is our point. Okay, and then it gives us another one. If f of x is 1 over 16, what is x? So this time it gave us the y value. We know that f of x is 2 to the x power. So we're saying when is 2 to the x equal to 1 over 16? So you can go back to what we did earlier, right? You could rewrite this as, well, 2 to the negative 4, right, is 1 over 16. So that means x has to be negative 4. Once again, what point is that on the graph? Well, that'd be the point negative 4 for our x. Our y value was 1 over 16. So negative 4, comma 1 over 16. Okay, then we have some limits. If you just looked at f of x equals 2 to the x, and you just did a quick graph, we already know that from earlier, it's going to look something like this. All right, so you could answer those questions. As x approaches infinity, looking at the graph, you can answer it. But I just want to kind of also show it this way. If we're saying that x is approaching infinity, we're basically saying, what's happening right here? It's 2 to the infinity. Well, that's a really big number. That's really big. So it's infinity. And you can look at your graph and see, well, as x approaches infinity, it's going to go to the y value of infinity. Well, the other one we can do is as x approaches negative infinity, which is a little more interesting. Once again, you can look and say, well, it looks like it's a horizontal asymptote that's starting to approach that y equals 0. So just taking it from this standpoint, evaluating limits more algebraically, if you will, we're saying, well, if our function is 2 to the x, what's 2 to the negative infinity? Well, that's the same thing as 1 over 2 to the infinity. There we go. Sorry, guys. So hopefully we got most of that. Just to make sure, I'm not 100% sure when that video cut off. So here's our point. Remember from 416. 2 to the x equals 1 over 16. So we would say, 2 to the x is equal to 2 to the negative 4, just what we did earlier. So x is negative 4. It's the same point, negative 4, comma 1/16. And again, the video may have captured this. Sorry, I just noticed that my phone went out. Hopefully it got all of those. Just to evaluate the limits one more time, if you had your graph, you could see it. Otherwise, you're looking at just plugging that infinity in to our function, right, to our 2 to the x power. So if you were to plug in infinity to the x as the exponent, 2 to the infinity is a really big number. All right, so it's going to infinity. You can see it graphically if you just did a rough sketch. But the negative infinity one's the more interesting one. If we're saying plug negative infinity in place of the x, you're saying what's 2 to the negative infinity, which is the same thing as 1 over 2 to the positive infinity, which means our denominators are getting really big. So you're talking about 1 over a really big denominator, which is 0. And I apologize once again. Hopefully that captured everything in that piece. And just to kind of make sure, let me go ahead and show all the problems again. Then we'll move on to number 2. So there's part A, 16. There's a point for part B. And then there's our final parts. C, D, E, and how about we call that F instead of D? All right. All right, number 2 on the mixed practice, g of x is equal to 5 to the x power minus 3. So g of negative 1, that would be 5 to the negative 1 minus 3. Oh yeah. So we got some fractions here. So 1/5 minus 3. Let's get a common denominator. What's that going to be? 15 over 5. So then 1 minus 15 is negative 14. So negative 14/5. Hopefully you can see that. All right, the point from part A, negative 1 comma negative 14/5. All right, g of x is 122. What is x? So 5 to the x minus 3 equal to 122, because we're given the quote-unquote y. We're looking for our x. Add our 3 over. Well, 125 is the same thing as 5 to the 3rd power. And just to kind of keep things a little more organized here, or at least clear, x obviously has to be 3. Because we have that same base, need to save the share, the same exponent, so x has to be 3. Our point, 3 comma 122. Then let's look at our limits. Once again, you can think of it as 5x minus 3 in the graph. I'm going to kind of approach it a little bit from the algebraic standpoint here. So it's 5 to the infinity minus 3. So we're talking about a really big number, minus 3. So there, 3 is, rather irrelevant. So it's going to continue to go to infinity. And then the last one, as x approaches negative infinity. So that'd be 5 to the negative infinity minus 3, which is the same thing as 1 over 5 to the positive infinity minus 3. Well, 1 over 5 infinity is just 0. Minus 3. So the limit is equal to negative 3. And I don't typically write it like this. I usually would probably write it more vertically, but just kind of making it where paper saved a little bit. But either way, you can see that this first one's infinity, and our second one is negative infinity. So let's look at our last problem now. So our last one's, like I said, is going to be a piecewise. So what you can do is you can go over here, you can make tables if you would like. There's nothing wrong with that. You can make a table for e to the x and e to the negative x like we did earlier. We've done e to the x already. We know it's going through 0, 1. And then it would go through 1, remember 2.718, so on and so forth. And one mistake I've made here, let me make sure I don't get ahead of myself here, and I apologize. Let's look at it from, let me do this. I don't want to throw this off. So for that piecewise, and I apologize, I just want to make sure that I don't get ahead of myself like I said earlier. You have e to the x and e to the negative x. And this is if x is greater than 0, and if x is less than or equal to 0. Let me double check that real quick. So making our graph, I'm going to look at the e to the x portion first. So for x greater than 0, we know it's typically a point at 0, 1, but it's not inclusive. So that's going to be an open circle right there at 0, 1. And then it would, of course, go 1, and 2.718, so on and so forth. And it would start to climb from like our exponential standpoint, like we did earlier, just that parent function we worked with earlier, the e to the x. Now, you could go ahead and make an e to the negative x table, like I was saying before, or remember that negative just does a horizontal reflection. So it's just going to take everything we have right here to the right, the portion we graphed, and just reflect it and regraph it on the left. So you're going to have that negative 1, 2.718. Now, the only thing that's different about this one is, it does look like this, but it's also going to, since it's less than or equal to, it's going to include that point now. So our graph does kind of come up. It's not quadratic. It kind of looks quadratic, but it's not quadratic. Remember, it's exponential on the left side and the right side for that problem. So there's our piecewise. I'm trying to remember what exactly I was having you domain, range, horizontal asymptote. So our domain, our range, and this is number 3, by the way, mixed practice. Horizontal asymptote. Okay, so domain, everything, all real numbers. So negative infinity, infinity. Our range, well, it's going from the y value of 1 up, so that's inclusive, 1 to infinity. Horizontal asymptote, we don't have one. Then it said, I think I wanted you to do also the limit as x approaches infinity of our function and negative infinity. So you can see as our graph goes to the right, it's going to go up forever. As our graph goes to the left, this negative infinity one. Sorry, I get a little sloppy here at the end of these notes. So as x approaches negative infinity, it's going to go to infinity as well. So hopefully that clears everything up on exponentials. As always, if you have questions, let me know. Stay out of the trees.